Let's start understanding the type 3. We have finished up type 1 and type 2. Let's jump into understanding type 3 partial fractions with quadratic factors. And before we actually start solving the problems, like for any other types, I give some context and gave some background on how to think about the partial fractions and getting the basics right, because in partial fractions, the only trick that might work or that you need to get right is the first step, where you substitute the constants based on whether it's type 1, type 2 or type 3, and we have not seen type 4. All the first three types are proper fractions, and we already know that, right? So let's get the basics first. Let's understand what is the trick that we need to apply and what is so specific about the quadratic factors. And in the next episode, we will apply those learnings from today's episode and solve the problems. So let's get started. So I've taken 3 examples and I will solve one example or maybe 2 examples in the next episode. So if you take these 3 examples, I've taken this and I think these are exam problems, and I've kind of rewritten it for better clarity over here. And the first and foremost thing is, which is kind of a recap, which we have done in in the episode which talks about different types of partial fractions, on how to identify what partial fraction or belongs to what type. So as a quick recap, let's do a quick recap on this one. So if we take these 3 problems, the first thing is to identify that this set of partial fraction problems belong to type 3, which is type 3 partial fractions with quadratic factors. And what does it mean? So let's try to see what is the commonalities between all of these 3 particular expressions. All the expressions are proper fractions. We know that degree of numerator is less than degree of denominator. We know that. So that's a good thing, because type 1, type 2, type 3 are all proper. We have not done improper yet. That's type 4. The denominator on each of them, there is at least one term in the denominator or one factor in the denominator which is quadratic, meaning the degree of the x power is 2. The direct power of degree is 2 over here. Okay. And that's what it's quadratic all about. If you see here, x squared plus 4, x squared plus 1. And the other thing is, none of these quadratic denominators that we have, or none of these quadratic factors in the denominator that we have, can be factorized any further. For example, x squared plus 4 we cannot factorize, x squared minus plus 1 we cannot factorize. And if you remember in the last video, it was not x squared plus 1, it was x squared minus 1, that we could factorize as a square minus b square, where we can call it as x plus 1 and x minus 1. So although it appeared to be quadratic, or it was quadratic, we could simplify them into 2 linear factors. But in these cases, none of these factors in the denominator which are quadratic can be simplified. So that's one thing. Okay. So that's how you identify that it belongs to type 3 quadratic factors. That's quite kind of a quick recap. Now, before solving these problems, let's understand some of the nuances. Like I said, the most important step, all right, the most important step in partial fraction is the first step, where you identify the type of the partial fraction and try to substitute the corresponding constants, like how many constants it will have based on whether it's type 1, type 2 or type 3, or maybe in the future we'll talk about type 4. So that's the most foundational and most important step, or the only step in which the whole partial fraction is based off. And once you get that opening step right, the rest of the partial fraction is all about mathematical, simple algebraic expressions or computation. So we don't have to really break our head on that one. And that's the reason I emphasize a lot, or put a lot of time on how to think about the first step. And I give detailed explanation for that. So likewise for type 3, we have done the same for type 1 and type 2. Likewise for type 3, let's get some intuition on what exactly is the first step and how do we think about that, and then let's get started. So to do that, like we did in the other types, what we will do is we will do the opposite of that. Instead of starting from a rational expression, we'll assume that we have a partial fraction and we are going to solve it or convert that into a rational expression, and understand what are the steps that happen in between, and then reverse engineer that and apply that when we actually solve these problems where we need to start from a rational expression and get into partial fraction. So we'll go back and forth on this one so that we understand the nuances of what's exactly going on under the hood. Okay. Now let's take the first example. Let's say we have a partial fraction. We have been given a partial fraction, which is opposite of what we exactly do when we decompose into partial fraction. And our objective is to find what is the corresponding rational expression for this particular fraction. Okay. So we have got 2 terms. This is term 1, this is term 1, and this is term 2. Okay, we have got two terms and let's solve it. So by simple cross multiplication and taking the LCM, this is no rocket science. It's basic maths that we have done. By taking the simplifying it or cross multiplying it to make it one single rational expression, we take the denominator, we do the LCM and we cross multiply. And once we do that slow and steadily, I put all the steps here, we kind of end up at this rational expression, which is boxed in the green color. Okay, so what does it mean? If I reverse engineer, let's say if I were given this partial fraction or this rational expression to start with, sorry about that, if I were given this rational expression to start with, this is the partial fraction that I would have got, which is what I've kind of summarized at the bottom. So we start over here from a rational expression, which is what we kind of computed in the previous steps, and the corresponding partial fraction is this breakout. And if I substitute the constants and put variables ABC for each of the constant, this is what I get. So for this, I substitute one constant, which is A over here. And again, we have this expression. So you can assume there's a constant 1 here, which could be B. Over here, I put B. Okay. And this is B. And the last constant is C. So this is how we substitute. Okay. No big deal. Okay. Now let's take another example, similar example, which is almost similar to this example. Okay, and let's do the same exercise. We'll start from a partial fraction, let's get to a rational expression, and let's go in the opposite way. Okay, so if this is the partial fraction I have, I've got two terms. There's term 1 and there's term 2, and my objective is to get the rational expression for this partial fraction by doing simple cross multiplication and taking the common LCM or multiplying the denominators, which I do step by step, and no big deal. And finally what I get is I get this particular expression, which is the corresponding rational expression for this partial fraction. So if I do the reverse engineering, so what does it mean for this partial fraction, for this rational expression? What is a partial fraction? Obviously it's going to be the same thing that we started with. So I'm writing this in the opposite way, or the actual way that we should solve for partial fractions, where we start with a rational expression and decompose it into partial fraction. And if you see here, again, I'm doing the same steps. I'm substituting the constants for variables. So this is A over here, and this has been C. I've intentionally excluded B, and which you will know if you understood my type 2, you will understand why I'm doing that. So we have got C here. It doesn't matter what you call them, whether you call A, B, C, it doesn't matter. It's a constant, right? You can name anything that you want. So, and we can call this as equation 2. Now we have solved both the examples and we have got two equations coming out of that. Okay. Let's see how, when we compare both of them, for ease of understanding, I've copied the equation 1 again, and let me erase that, make sure it's clear. Okay. So we have equation 2, and from the above example that we composed, we have the equation 1 that I've copied from the above example. So I've not made any changes, and let's compare these two and see what we observe. Okay. So let me take you to the observation notes. Okay. So if you see the equation 1, which is this equation, okay, this equation 1, both the examples are quadratic, type 3 quadratic. Okay. Remember that. But equation 1 has this extra factor, which is the bx part of it, right? If you see there is no bx or there is no factor with an x coefficient that we have. And the numerator in this equation 1, this whole piece, you can think of that as a polynomial by itself, where you have the x and the constant term and all those things, like how you have the x and the constant term here. The numerator also is a polynomial in the descending order of x. If you see here, I put x raised to the 1. And then this constant is 0. So this is as good as x to the power 1, and this constant is x to the power 0. That's what it is. And the overall partial fraction, this overall equation, the final answer has got three constants like a, b, c. That's what we observe. Now let's move on to equation number 2 and see what we observed there. Okay. For the same type of problem, which is quadratic factors, let's say the overall partial fraction has only two constants, a and c. Okay. Whereas the equation 1 has got three constant. And again, we can think of this constants as polynomials, like how we thought here. This is over here, it's very evident because you get this x factor and then you can mentally understand this is a polynomial. But like I said, this is a rational expression, which is nothing but a ratio of two polynomials. And similarly, when you do the partial fraction, you should assume that each term is a ratio of two polynomials. Whereas in this case, it's only constant. So you might forget that, but basically it's nothing but a x to the power 0, c x to the power 0. So there's nothing but this is also a polynomial with a constant, and this x to the power 0 is implied, so we don't write it. So it's again the same thing, but there is no term which is this term, this bx, right? Bx to the power 1. There is no term like that. All are constants. That's one fundamental difference. And there are only two constants, a and c. And whatever I've written in red, just keep that in mind. So by now we should have the notion of thinking of every type 1, type 2, type 3, or any rational expression, right? We should think about the notion of every numerator. Doesn't matter what type it is. It's a polynomial of varying degrees, and all are proper fractions. What does that mean? The numerator degree should be always less than the denominator degree. If you see here, the numerator degree is 0 and the denominator degree is 1. So denominator is greater than the numerator. Same way here, the numerator is 2 and the denominator degree the denominator is 2, sorry, and the numerator degree is again x to the power 0. So that's always there because it has to be a proper fraction. It cannot be improper fraction. But you should think about each one not only as a constant but as a polynomial with varying degrees, right? Based on how it is defined. In this case, it starts with x to the power 1 and then it's in the descending order. Over here, it's just a constant, but still it's a polynomial. So we should start thinking about that. And once you apply that concept for all the types on how you define the constants, and think behind the head that basically when you put the constants, you're putting a polynomial based on which it might have a power of 0, or it could have a variable of x with a power of 1, or it could have a variable of x and a power of 0, and all these are just coefficients. So you should think from that standpoint. Okay. Now, the $1 million question is over here. The $1 million question is, when you in the exam or anywhere, when you have been given a type 3 problem, let's say you identified a type 3 problem correctly and you want to get this opening step, because like I said, this is the most important step over here, like I've highlighted here. The most important step is this, getting this to this equation 1. Like, how do I start from this point and substitute this and then solve? Similarly over here, both the steps are the most important step, and for all the partial fractions, this is the opening step. So getting this right is very important based on the type of the partial fraction. So the question is, I had both these problems, example 1 and example 2 are type 3. I know that I've identified it correctly. But in one example, I'm just taking two constants, just plain constants. In the other example, I'm taking three constants, but with this construct of a whole polynomial where we have we have a coefficient, and that's associated with the x with the power 1. So how do I know in advance when should I use this scenario and when should I use this scenario? That's a big confusion, right? Because getting that right is very important. Okay. And that's your $1 million question. Like for type 2 quadratic factors problems, what constant term should we assume? What's our opening step, the most important step? And the trick to that is very simple. Like the same thing that it's kind of parallel to what we did in type 2, where we brought in that extra constant term, right? So what we will do is we'll always follow the pattern in example 1. What does it mean? We will not follow this pattern. We'll always assume, regardless of it's required or not, we'll always assume that we have to put three constants, okay? And in this format exactly. So whatever is the linear term in the denominator, that will just have a constant by itself. You can think of this as a multiplied by x to the power 0, just a constant. And whatever is a quadratic term, when you separate that out, you put this construct as if it's a polynomial, but it starts with the degree 1. So bx plus c. So totally you'll have three constants based on if there are two terms and one is quadratic, so you'll have three constants. So one constant for just the linear factor, and for the quadratic term in the denominator, you'll put this construct as if it's a expression by itself, bx plus c. So that's the first thing you will do. So you will not follow this construct, you'll follow this construct regardless of any of the type 3 quadratic problems. That's the first thing, right? And what you can think about that is, the numerator should, like I put here, assume the numerator for the quadratic denominator, wherever the quadratic term is there, it will be always bx plus c, kind of this construct you'll put. Okay, sorry, this construct over here, you'll put that. Okay, and it's obvious that you see that the degree of this x should be 1, because here the degree is 2 because it's quadratic, and we need to make this a partial fraction. So the degree of this x cannot be 2 or more. It has to be 1 less than this. That's obvious, right? So we have seen that. So that's the first point, to make sure that it's a proper fraction. And this is kind of similar to how we assume the extra term with a constant for type 2 repeating linear factors, and we solve that. If you remember, we just brought in, whenever the factors were repeating, we brought in an extra term for that. If you don't recall, just check out type 2. Okay. And like I said, the notion, think of each individual term in the partial fraction as a rational expression. Okay, what does that mean? Think of each of these terms. These are terms here. These are terms, right? These are terms here. So think of each of this term, okay, as a rational expression by itself, where you have a polynomial in the numerator, we have a polynomial in the denominator, and overall it's a proper fraction because the degree of denominator is greater than the degree of the numerator. So get that concept here. The same thing that I'm repeating here. Okay, that's one here. And what should we do is, like, for the term which has a quadratic polynomial in the denominator, that means this particular term has a quadratic, the degree of the numerator will start with 1 degree less, which I have told, and then you will complete it all the way through the constant. For example, if I write a polynomial here like this, let's say x cube plus x to the power 2 plus x to the power 1 plus a constant which is mean x to the power 0, and this is a constant term, right? Okay, so you see the powers of x are descending all the way till we hit the constant. This is the constant. This is the constant mark. So you have to apply the same concept. So the quadratic term in the denominator is x to the power 2. For this, the corresponding numerator, you will start with 1 degree less. We will have this extra term, and obviously this might have any coefficient. In this case we have 1, but we don't know that, so you'll put a coefficient for that, and you'll go in the descending order all the way through the constant, like how we have it here, where the degree of x is 0 or it's implied, we don't write that, and that's what we need to do, and that's what we will do here, right? For the term which has a quadratic polynomial in the denominator, which is degree is equal to 2, assume its numerator polynomial starts with 1 degree less, which is degree is equal to 1, than of the denominator, and ending all the way through a constant c, which is pretty much you write the whole expression like I said you. Like, let's say if you have a polynomial like this, this is how the polynomial appears, right? Where the x's are arranged all the way through constant. So take it all the way through the constant. Okay, that's one. And then the last step is, if your assumption, we don't know, because in this case, this concept, let's say in this case, let me get this some real estate here. So if you see in the above equation 2, if you see the above equation 2, the bx was not there, this term was not there, so it was basically 0. But in this case it's there. We will not know, but we are always assuming that this is going to be there. So if it happens not to be there, let's say if you assume for this problem, if you assume bx plus c here, and if you solve that, eventually bx is going to be 0, and then what you will get is just c. So it is going to be possible that if your assumption is wrong, the bx term will become 0, and that's okay, and then we'll just left with the constant term. Okay, but we'll not know that upfront, and that's the reason we'll always assume that this is going to be there. Possibly there's a quite possibility likelihood that this is going to be there. That's a fair assumption, and that's how you're going to get the right answer. If this term exists, like we saw in the other equation, the equation over here, equation 1, you will get the value of that, because you see the value of b here is 1. You will get a non-zero value. If the assumption is wrong, you're going to get this 0, but nevertheless you still get the right answer. And that's kind of the nuances of how do you need to substitute the very first step for type 3 partial fraction. And in the next episode we'll solve some of the examples, but I just wanted to set the stage on getting the trick right on the opening statement or opening equation, computation or substitution of constants for type 3 partial fractions. I'll see you in the next episode.